Thank you, and I'm very sorry for all the messing around. Yes, I'd like to point out that this is part of what I believe is a coming major change in the field, in which cognitive constraints come into focus. And I've been thinking about this for um, up 20 years or so, 25 years, and the book that's recently been written summarizes a swing in my approach to research. It's relevant background to this paper because what I'm going to do in this paper is essentially introduce aspects of cognitive economics into the analysis of machine learning. And what exactly that means, I'll unfold it for you. And this happened in large part as a result of the fact is it's good timing that cognition is more central now that AI is coming around. I realize that the constraints are on understanding are joint as between a human and a machine, but that the framework, from what I can tell, should always be the economic framework. So there's a big claim here, which is
Yes.
machine learning is studied by engineers, and boy, they're doing well. I'm not disagreeing about that. But that they literally don't understand the economic model of learning, that they would benefit tremendously from having a better understanding of it. And that way they would be better set up to help humans and AIs work together in the service of better understanding. So what I'm going to do is describe one small piece of that logic, a paper Misaligned by Design, Incentive Failures in Machine Learning, with David Autor, Daniel Martin, and Philip Marks. And it's a continuation of the paper Modeling Machine Learning for those who'd like to look at it, which makes the associated claim that it is worth thinking about a machine learner just the way we think about a human learner. And we think about them as learning through signals and updating, and that thinking that way for a machine learner is valuable. And I'll show you a little bit now the particular context. So the way we're going to treat this is to think about high stakes decisions in which AIs are used, and think of contexts in which error costs can be asymmetric, which is false positives and false negatives can be a very different damage to the to society, and therefore one wants to think about learning specific to the human objective at the end. For example, misdiagnosing pneumonia when it's absent is inconvenient, but failing to detect it when it's present can be life-threatening. So there's a lot of talk and chatter about AI systems should be in line with the intentions of their human deployers. And there are all these fun analogies of, you tell an AI to maximize the number of paper clips, you forgot to give it the constraint that it shouldn't eat up human beings, and it ends up turning us all into paper clips. So that's Bostrom's analogy of how an out of control AI, if you don't give it the proper objective function, can do great damage to humans. And the answer in most ways of describing this problem, Stuart Russell, for example, is to have the AI learn the human values, and then we impose the human values on the AI. And in a simple way of doing that, you might imagine improving alignment of the AI by giving it a loss function when training that reflects the human values. And that is, in fact, widespread practice. And I'll go over an example that is a motivating example in what we did. And that gives rise to what we call the aligned learning premise, which is if you train on the human objectives, you're going to get the machine to better align with those objectives. And their common implementations involve imposing the weights in the training process, even in the sampling process. And we find that this is not a good approach in two particular applications. And in those two applications, although this is not the general model, it's better to train without accounting for the human objectives and to apply the human objectives ex post to the model predictions. Now, we know that is in fact practice sometimes, but we also know that there's no principles involved. Often things are seen purely engineering terms, and we're going to say that there is an actual analytic content that should be thought through. And the analytic content comes from the economic theory of learning. All right, so our focal applications are pneumonia diagnosis with chest X-rays using the architecture of deep neural networks. This, one thing I want to comment on, and it's very disturbing, is that economists could be making many more contributions if the data sets weren't locked away from all public access, except in the rarest of cases. So the fact is that if there was openness to the proper input, we'd find the problem that we're looking at here is widespread, but instead we had to go scrape around, beg, steal, and borrow to find a couple of examples in which there were data sets we could actually use. It's really quite sad. So we used pneumonia diagnosis with chest X-rays, and we used CIFAR, very different types of architecture. And in both cases, we found that unweighted training and ex-post adjustment outperformed utility-weighted training. And I'm going to give you a little technicalities on what we mean. But let me first indicate, just to show you, it's nothing to do with how long you train, the losses are higher, the red line, the losses are higher when you use the weights than when you use the unweighted and then adjust afterward. And the adjustment is actually theoretically motivated, as you will see. Let me just go over. So here we are. There's clearly something to be explained. And why is this happening is an interesting question. But let's first back up and make this an analytic system, because we're going to actually think of this in the economic sense as a learning problem, where there's going to be an assistant in the learning, and the assistant is going to be the AI. And there is somebody, a human, we're calling them a machine learning engineer, who's trying to deploy the AI to help them with a final decision. So what we're going to input is a set of X-rays on the left-hand side here. And we're interested to know whether these X-rays indicate disease, and if so, what type of disease. And as a function of how likely it is assessed to be that each of these X-rays has a particular condition, Y, we will offer, the idea is that this is the advice offering module, which is a little bit of a black box. Something operates between an X-ray and the advice on the basis of that X-ray. Let me keep going, okay?
Yeah.
Okay, so I'm so sorry. Understand what's going on. The job here is that somebody, an engineer, wants to use an AI to give advice. And to do so, they have various levers at their control. We know it's an economic problem because the utility function assigned at the end. The utility function tells us how good it is to give each piece of advice in each of the various truths. So that's the literature. This is about kind of important diagnosis. And what we're going to do is actually have an AI model that is going to produce probabilities. It's going to input the images from those it will output for each image how likely it is to be of each of the underlying true types, that is cancerous and not cancerous, etc. After that, there might be some adjustment made by the engineer to give advice based on the machine output. But the key thing is that we're trying to get this to be aligned and to be a very good prediction function F, that once you've got added delta to it and post-processed it, you have maximized the utility of the designer. So the designer has a very clear problem. They'd like to understand classifications well enough to give good advice. And that's the game they're playing. And they deploying the AI model specifically to help them in a human objective. Now, since we know the human objective, we're going to ask ourselves, how exactly might they train the AI model? And that's our key question. The idea is that there are many different loss functions that could be used for training the AI. And that's where often the machine learning engineer will have a great deal of control. What loss functions should they be using to train the AI? And one thing they could do is to say, well, I'm going to treat all losses equally as I'm going to get the AI, the machine learner, to have a pretty much minimize the expected number of mistakes type logic, and then learn and then spit out some probabilities or some output to me, which I will adjust and then decide what advice to give. The key choice, therefore, from an economic perspective, from a decision theoretic perspective, is the choice of the loss function L for training the AI model. And that's what we focus on. So the idea is always it's constrained learning. If the machine learner could do everything perfectly, then we would just tell you exactly which is what you have pneumonia, you don't have pneumonia. But even the machine learner is constrained, and therefore it's going to look like a constrained learning machine. And we know that. What do economists tend to think about when they think about constrained learning? Well, they tend to think about costs of learning. And so is it the case that the machine has underlying some costs of learning, and then it has incentives for learning? So we're now going to think about the AI exactly as we would think about a human learner, as a function of the loss function with which it is provided. It creates a form of learning that is a Blackwell experiment in response to the loss function. And that Blackwell experiment, the standard economic object, is produced according to some inner machine logic that connects the L that is provided to the nature of the learning that is done. The aligned learning premise says, if we want the machine to respect, let's say, a very asymmetric concern about misclassification of pneumonia cases, in which you'd much rather err on the side of saying it might be and do something about it than not, then that should impact the loss function that is asked to minimize in the process of training. So, and that would be the aligned learning premise. But there are, in fact, two things, and our approach says there are two things that the incentives do. First off, they tell you, the AI, it tells you, given any bit of learning that it was done. So we think of this, we think of the AI, unlike most people would think, we think of it just as a standard learner. It comes up with a Blackwell experiment. It therefore comes up with something that might be an internal posterior. That's how we're going to think of the machine. When it has done the learning and come up with this posterior, it also chooses a prediction. It says like, okay, well, given what I learned, I don't know what it is, but now it's 98% likely that that this image indicates pneumonia, and I'll give a score according to 98% likely. Or it can say it's 10% likely. And I've been told by my loss function what to say when I think something is 10% likely. The loss function has an impact on the report that's offered, actually. So not all of these are what are called proper scoring rules. And an AI, having learned that something is 0.1 likely, may face an incentive in the loss function to misreport that as 0.98. And in fact, when you're doing training with an asymmetric loss function, you are incentivizing the machine to exaggerate the probability, because it says you don't want this 10% is not something you want to think about. You want to think about bigger numbers and more likely to be. And so I'm going to distort my report. The distortion of the report is separate from the actual amount of learning. And the key issue is that learning is in fact endogenous to the loss function. This is what modern theories of learning say. And this is what the entire basis of decision theory of learning is. Depending on your utility function, you learn differently. And what we're saying is, depending on the loss function that you fed to the machine, it learns differently. And in fact, if you're not careful and you pick something that the human really thinks is a great objective function, the appropriate response of the machine is to learn less. It actually becomes a more poorly informed machine because of an instruction you gave it inside the loss function. The loss function in particular dictates the shape of the gradient. So here's the illusion one might have. The illusion one might have is that regardless of the loss function, the AI should just learn as well as possible and then give a report. Just learn well and then tell me about it. But that's not the way it works mechanically. When you put a loss function in, it actually impacts the gradient in the learning process, therefore impacts where you end up. And what the asymmetric weighted loss function does, you can do your choosing perfectly correctly, but it distorts your learning, and you are therefore misaligned by design. And here, in fact, we're doing this very technically. In the paper, you can see exactly the mathematics of what we're doing, using weighted entropy as was used in the particular paper on pneumonia that we're building off. It turns out that if you regard the machine, so I understand it's regarded in the AI community that Bayesianism was thrown away long ago. In terms of the machine having to do anything Bayesian. It doesn't. Computing Bayes' rule would be much too costly along the path. So it just does stuff and produces output. And the output turns out to be incredibly valuable in decision making. So congratulations, it won. But if you think of it as we do, as it were, at some point having had a posterior, and then you give it an asymmetric loss function, it will misreport. And the first thing which I'm showing you here is that if you put in a weighted loss function exactly the way that was done in the paper we're imitating on pneumonia, then the AI, if it has a posterior belief, if we model it and think of it as having a posterior belief of something like 0.05, is being told report 0.85, that's the red line. It is in fact being told that if it's as if, because it's all an as if model, as if this was a Bayesian learner, as if it had come up with a posterior, it would have been told, don't give me the posterior because I don't like the number 0.1. I'd much rather that you say something because I don't really care about the errors where you said a high number and it turned out to be wrong. That doesn't matter to me. So if the machine says, okay, I don't mind saying a high number, even if it's really 0.1, I'm going to say 0.95. And so you get this tremendous compression in the reports, which is almost everything comes out looking like it's quite likely to be pneumonia if you, it's an optimal prediction. You know, it reports everything very high. And of course, you might want, as a downstream, you'd say, I don't want to use your distortion, so I'll undo that. But the damage, you can't undo it because the damage this did was in the learning incentive. So what happens because of that is that, in fact, you have incentivized very little learning. And if you look at the blue line was the unweighted learning, in which case with the unweighted loss function, the optimal report was what you believe in the Bayesian sense. It's a proper scoring loss function. It's optimal to report what you believe. And you'll see that the incentive to learn, the marginal learning incentive, is extraordinarily low with the red function, with the distorted. It's telling you that it wasn't really very valuable to discriminate between, let's say, 0.25 and 0.75, because you reported them all as 0.999. That was that learning turned out to be of very little value given the loss function you provided the machine. Whereas if you provided equal weights, it was valuable to learn throughout the entire belief posterior range. And in fact, there's an even more telling figure, which is the overall incentive to learn. And what's happening is, I can tell you that in general, the incentive to learn provided to the machine is much stronger when you use the equal weights than when you use the very unequal weights. And I can point out that it's not quite true, because if you went very far left in that picture and took an extreme microscope, you would see that the incentive around 0 is a little bit stronger with the weighted training. What it's doing is telling you you'd really like to move away from 0. That's extremely valuable. But everything else is not very valuable. And the end result of that type of incentive seems to be largely, most likely responsible for the ultimate failure to learn well with the asymmetric weights. What I showed you before, the learning is not good with the asymmetric weights. It's better with the symmetric weights. And we think that is mostly because of a very classical economic notion, the value of learning. And the value of learning is what an economist thinks about when it's the Blackwell logic. The Blackwell logic says there is a decision to be made, and of course you wish to learn, and but you do so based on how much that learning lifts you above the decision you would have made prior without the learning. And that's a very classical piece of economic apparatus. And it says applying and thinking about that classical economic apparatus in the context of machine learning has more value than we knew. And the intuition that, it's a good idea to use the weights that reflect human values is simply naive. It's not what we would be doing if somebody said design this optimally. We would be not claiming that the very best is to have unweighted, because we don't know, but that this is a frontier in which you need to understand the mapping between incentive structures provided to the machine and the extent to which the machine actually effectively learns. And, there's a large literature that's beginning to be connected to in economics, but that's not my concern. What I would like to do with my remaining time is explain why I think this probably applies also, maybe even stronger, to large language models. And that's something, because large language models, are themselves reward-based. They are based on the human feedback, so the reinforcement learning with human feedback, which is, again, a different version of I'll punish you for certain things rather hard. And for example, the most obvious thing might be that if you tell the machine, and I think everybody's aware of this, but it's not systematized, if in the reinforcement learning, humans respond not very well to harsh comments, then it's very likely that you're going to have a bland AI telling you that everything is good and there are multiple trade-offs and, never say anything bad about anything. So everybody's aware that you have to trade off this kind of avoiding of human discontent with the responses against the actual learning content. But what might not be realized is the AI might not know stuff because it's blanding itself out. So the larger point is that I don't think there's any stage of what might be called a human AI decision-making pipeline at which you can avoid the human being. And I think we've done too little of that. We've done too little of include the human being in the picture, modeling and measurement. And the ultimate, and I continue to believe that the economic model of learning is effectively the only model of learning that functions in terms of helping people make better decisions, which is going to be the goal. And my own take is that in the longer run, there'll need to be a soup to nuts reorganization of the human AI understanding to be much more joint. And the engineers should be working much more tightly with those who study the economic model of learning and think about it. And we should be gathering data in a richer way, a little bit the way we're doing it here. And I can tell you that some of what's being done in this paper is an outgrowth of earlier work on cognitive economics that Daniel Martin and myself and Mark Dean got involved in for entirely reasons that had nothing to do with AI. It had everything to do with humans and costly learning. But I think that the mapping and the analogy in the AI space is essentially perfect. And that's what led to this research. So I feel like I've been very interrupted, but I don't think I want to say much more. And I'm open to questions. Oh, I'm open to questions. Let me do that. And I'll stop sharing my screen. If that doesn't cause my entire thing to crash.
Hi.
Hi.
Can you listen?
Yes, yes.
We can hear you. Yeah.
This is fantastic. I'm not sure you can see me. I'm on the high-speed train. But you can hear me now, right?
Yes, I can hear you. Absolutely.
Yes, Andrew. So this is fantastic. So I think it's almost the first time I think I listening to AI papers, but I think it's the first time that I see this is getting up to a philosophical level to talk about a very fundamental thing. So basically, it reminds me of when we think about philosophies, essentially we have several layers. One critical question, of course, is what's the essence, what's the nature of the things? And then another thing is the moral philosophy. So which stand should we take? I think if my understanding is correct, that you find that inevitably AI is encountering these two problems mixed together. So essentially, for any human beings, we have our moral stance. or preference, and they also want to know the nature of things. But then for the AI itself, when these two mix together, it kind of limits its ability to learn the nature or what takes the stance. Or thinking about social science in general, there's no absolute truth. In social science, it's all about stories, and the historians told us. And so in AIs, I believe you tell us that AI will be inevitably wrapped in some kind of story, take some stand because it's a social science. It's wherever it made predictions. So I think that's the nature of things. Anyway, so I think that's profound, and I think it's hard to dispute. The question is, what can we do? And I think and I'm trying to hearing what you think the best way to go ahead. What makes this clear is that every AI is an expert like humans. They have the and they're going to have their analytical abilities. The questions, and even think about the chat bot or advisors to us. They're going to advise a lot of things. Are they advising this objectively, or are these advices aligned to our objectives of our preference? Anyway, so I think the question here is it's there. I would like to hear you to talk a bit more about what can we do about this, and which type of questions, and what context, which type of issues this is less serious, and which type of issues we have to deal with differently. Probably that's more constructive. Thank you.
Well, thank you for those comments. I'll give you a perspective that might or might not you may or may not agree with. I thank you for all the praise. I'm not sure that I'll tell you that I'm very operational. The approach I have is very much that what we need to be doing is gathering ideal data for models of learning, and that so there's the first layer is engineering the type of data that will allow us to understand the operation of an AI as a learner and its interaction with a human as joint learners, and that the classical model elements, we will need all of them, and we'll need many, many more as we gather richer forms of data to understand why machines learn what they do, what their vulnerabilities are, why we believe what we shouldn't believe from them. But I am very much doing this in the sense of a science and in the hope that there's external validation. Everything must be tied to data sets. And the data set here that we're using is the joint output of some notion of ground truth and what the machine says. And it's that joint notion between ground truth and what the machine says that tells you how well the machine is able to learn. And so therefore, I do exist in this rather constrained box world of ideals. The ideals are built from models and then inform models back in the converse direction. I'm not sure if I helped you in any way, but that's how I'm thinking of it.
I think it helps a little bit. I think it's almost true that it motivates us to think that we need to need to let AI to learn more objectively before we impose preference on them. Probably that's if I understand this correctly. But I think in many contexts, it's much harder to separate them. if you are doing medical training or other stuff, I think there's certain, let's call this true probability there, and you should let it learn stuff like that. I think I get that. But in many social science contexts, in business decisions or a lot of things, um, it's much harder to separate those things. And I think you gave me the stimulate me to think that and so AI will be hard to it's hard to distinguish this more like a science approach with the incentive stuff. I think my point is that you probably really want to think this harder. It's make this much more useful.
Got it. Thank you.
I see Professor Joshua Gans has raised his hand.
Yeah, hi. This is a great paper. I'm very much enjoying this. Myself and J.R. Gall and Avi Goldfarb have been thinking about these where the utility functions should enter the decision process issues for some time. I want to say that the reason the focus on loss functions and tweaking them has an economic origin. Hal Varian has very proudly said for years that he pushed to Google to be more explicit about its loss functions and allow people to tweak them. And in fact, if you go to Google's machine learning tools, there's a loss function there which is designed precisely to do the things you're advocating against right now. But because not doing anything was also some version of an assumption about utility, if you were just going to take the prediction and just rely on it. But what's going on here is, of course, the AI model is generating a prediction, and then, of course, you realize you can do stuff with that prediction according to your utility function. The reason I think we end up in this situation where the engineers decide to bake in that is because it's very costly for people to do this. So in some situations, we've not been able to do it at all. For instance, if we've got a weather prediction, no one cares about the weather. I mean, you're English, so you maybe do, but no one else cares about the weather. We care about what are we going to wear today, or are we going to take an umbrella. Yet our weather apps give us all this information, almost basically the true version of the probabilities of the true state. Whereas most of us are not interested in that. We would be interested in knowing what we should be wearing, etc. The problem is that that has inputs other than the weather, which makes that prohibitive. So I think actually the issue, and Long sort of hinted at this, was there's sort of multiple economies going on. There's a sense in which I think it's really useful to point out that imposing a loss function constrains the information that's coming up. But I also think that that can be optimal in certain circumstances when you're economizing on either people's cognitive take for the prediction later on, would be the social science aspect, or on the engineering aspect that it's costly to learn itself. And in fact, it might be easier to concentrate on the margin of 0.1 to 0% than to 0 to 100%.
Right, but I would make the bold claim that right now nothing is being done vaguely optimally.
Oh yeah.
It's just being done.
Yeah.
And
No.
It's not like there's a profound logic and we're missing it. It's like
no. I mean,
this 0.99. I like it.
No, I 100%. And moreover, the training was designed, and whatever post-training was occurring from the humans was sort of reinforcing that. Well, I like this. I like it when it tells me.
I think we're in Happy Valley, not in not in the enlightened future.
But it's a complicated question in terms of I certainly don't want my medical doctors liking a result. I'm less concerned by the low stakes stuff. So it does sort of relate to how big these costs of errors are, really. as to how much effort you'd put into this issue, right?
Yeah, but I mean, look. So the claim is that when you decide that I'm 99 times more concerned with one mistake than with the other, so I'm going to put 0.99 in a loss function.
Right.
Your wires got crossed.
Yes.
Yeah, there are two statements. The only mistake was using the word "so" in the middle.
Right. Right.
It's like "and." It's like, so this makes the point that the logic of this link is very worthwhile. What I would do is I would take a few examples, run the heck out of them, and see if there are irregularities in why
Right.
the learning improves or gets worse, and maybe discover that there are issues with algorithm design that would have allowed it to follow the gradient better when you change. In other words,
Yeah.
study the loss, study the Blackwell system.
Yeah. Yeah. We don't even get that information. You're correct.
I enjoyed the discussion and presentation very much, but I'd like to add maybe a observation, because in the industry, actually, I mean, they probably, as Joshua just mentioned, know that the separation of learning and the decision is necessary. But there are obstacles. One is cost. The other is whether it's possible to separate an objective ground truth from the preference of a subjective preference. So whether it's doable, as Professor Long Chen just mentioned. So what we can observe is that actually, for example, for the medical examination, instead of ask the machine, the AI model, to report positive or negative, they actually ask the machine to diagnose the patterns. So whatever patterns is observed in a scan, in a picture, and report probability of this disease, and leave the decision to doctors. Because for medical decisions, actually the utility is not universal. So for example, for a patient with older aged patient, the decision to say whether he needs further diagnosis or need an operation is different from a young, say 25 years old. So in practice, they actually need to separate the utility function from the
All
diagnosis.
right, so let me answer that. The first thing is that the framework allows for it. It just says the advice could be something much richer. If you want it to be richer, it's richer. And then somebody downstream operates on it, but that's still but because you need to know as a designer the utility that ultimately will be assigned, so the doctor should communicate with you. Second, there's no excuse for not understanding, and I refuse to believe that the correct answer is for the engineers not to understand any of this, guess their way forward, and say we did it. And currently, the system involves exactly that. If you could show me that they've really understood this and they've internalized it and they're optimizing subject to some invisible constraint, then I'll back off. Until that point, my guess is they don't understand it. They do the engineering. It's great. It's good enough. Trust me, I use it a ton. But this logic is being bypassed, and I think it's a mistake.
So how about if the challenge is we cannot have a ground truth? We cannot actually separate the human utility from an objective ground truth. Say, let me think about it. Example, we actually have, for example, for the large language model example you just mentioned, they tend to please the users, and it's a big issue. But the difficulty is what is the correct objective ground truth if we try to still align human beings' preference, but still there is something in the middle, right? What is that? We cannot find that, right?
Well, I don't know. I mean, you know, you give me a context, a precise context, and
because I'm actually annoyed by the, say, ChatGPT or Gemini that he always please me. Because what if I made mistake? He'll just follow me, right? But I like to have a good agent that can correct me when I make mistake. But they are really bad at it.
Well, that sounds like there is a thing, which is that there's such a thing as a mistake you made and you weren't told about it. So you didn't say there wasn't a ground truth.
Yeah.
So you could judge that as having performed poorly.
But that's one of the big tasks for the alignment jobs in the companies, right?
But I agree.
Yeah.
I agree, but I don't think they're studying it in a manner that reflects the seriousness of the challenge.
May I chip in a little bit? So I think this is a really deep question. Recently I've been fascinated by reading sociology and some philosophy stuff. And it got me to understand why sociology exists outside of economics. And I realized that economics is very narrow-minded because there's a lot of the complications, especially when you compound it with the human preference, the psychology, a lot of incentive stuff. So I think this is a very general problem, and it exists. And I really appreciate your critique on the current engineers' naive approach. And
well, you haven't heard me going off on sociology yet, so.
Oh, okay. But anyway, so I just know that this is I don't think you're gonna get this done just from a scientist's point of view. But I think it will become, it is a critical issue, and I really appreciate if you can go deeper into which kind of type of questions, tasks that we need which kind of models take the stand on those things, because I think this will be the context will be everything. Yeah.
I agree with you. I would say there's a tremendous issue in that, I can do a lot of abstract thinking, but the number of people within the machine learning community looking to learn any of this is approximately zero, because by and large, they're too busy building super genius intelligence, which I respect hugely. I'm very happy with that. But they're very busy doing engineering things, and they don't really have time. They don't really have time.
They don't even know economics, and much less sociology. That's my point.
There's a lot they don't know, but it's working superbly. I get it. But,
right. They're changing the world without knowing a lot.
Yeah, exactly. So that's my perspective anyway. All right. I'm very comfortable. I hope that I was able in the end to get things across, despite our troubles.
If there's no more questions.
Thank you very much.
Thank you, Professor Caplin. Sure. And it's really a powerful reminder that maybe the computer science need to consider the fundamental economics of learning and incentives.
It wouldn't be bad if they thought about that.
Yeah. Okay. And thank you all for joining us this late. And,
okay, thank you.